Okay. Just starting, why would it be an issue if I said that this object is moving at a constant velocity? Krish. Exactly, it's changing direction. So when something's in what we called uniform circular motion yesterday, it means we're going in a circle or a partial circle or curve at a constant speed. We can't say constant velocity. Velocity is a vector, direction is always changing. So if it is going at a constant speed, that means it's not speeding up or slowing down, right? So is there any acceleration occurring if it's not speeding up or slowing down? Go ahead. Yes, because way back when we said there was 3 ways to accelerate: speed up, slow down, and change direction. So this is that special form we really haven't talked about till now, just noted way back a long time ago. And who remembers from yesterday the name of this acceleration? Since it's kind of special, at least because it's not in the speeding up, slowing down form. Anyone remember it from yesterday? Nope. Started with a C. Nope. Centripetal. All right. Centripetal means towards the center, and that's exactly where it points. So if we drew vectors for the velocity, it always points. We already said the velocity is constantly changing direction, right? At any moment, if you froze it, it's pointing in a different direction, right? And if we drew the acceleration vector that is caused by the change in direction, it would point inward. So I'll show both. And we also said yesterday that if we took away whatever is making this object go in a circle, how would it fly off? Anybody recall? There was a term I used yesterday that said it would fly off tangent to the path of the circle. And that means really in a straight line. The term tangent, as you may have learned in geometry, that means a line that touches a circle one place that's perpendicular to it. So if I shut off whatever's making this thing go in a circle, it would fly off in a straight line. We call that tangent, and that's why, I'm going to put it back in the circle, sometimes we call the velocity tangential velocity. All right, a couple other quick things. If there's an acceleration towards the middle, remember from way back when as well, that accelerations magically don't happen. Any kinds of them, no matter what they're caused by. Speeding up, slowing down, or changing direction. Forces have to cause accelerations. And if the acceleration's centripetal, then the force is centripetal. That means towards the center. All right? This simulation does not allow me to show a force vector, but if I could, the force vector would also point towards the center. So I gave an example yesterday using this thing. So, and this is the last big thing that's important before we move on to the math behind all this. When I swing something like this rubber stopper in a circle, if the acceleration is towards the center and the force is towards the center, why isn't the rubber stopper or any of the objects traveling in circular motion actually moving towards the center? Why does it stay on the outside of the path? Anybody recall that? Big hint, it's something that we defined in the past that is not a force. There's not an outward force. What force directly is making this thing go in a circle, guys? What's making this object go in a circle? What's physically touching the object? The rope. So tension, right? So the tension, that since it's centripetal in this case, is inward, as well as the acceleration, since it's centripetal due to changing direction. But my question is, if that's all inward, why is it actually moving inward as it swings? Why does it stay out here? Go ahead. Yes, but it's changing direction and staying on the outside because of this. Starts with an I. Yeah. Inertia. Remember, inertia is a property of something's motion to keep wanting to do what it's doing. Since this is changing direction, like you said, every moment, its inertia wants it to fly off. How does it want to fly off? In a straight line, right? Because if this wasn't there, that's what would happen. If this string wasn't there, if we released this string, it would fly in a straight line this way, right? And since the string's not letting it, it's kind of inertia and string are kind of having a battle. Inertia wants it to fly, string doesn't want to let it, but that allows it to stay on the outside of the path. All right? But just to be very clear, there is no outward force, because inertia is not a force. The only forces in circular motion are actually inward, causing this inward centripetal acceleration. So that, in a short few minutes, pretty much runs down everything we described yesterday a little bit more slowly. Okay? So with all that in mind, I'm going to flip over to the notes, and I'm going to post these notes, but you probably want to write these formulas down just to have them somewhere in your notebook. No. Why is that there? One sec. Something's not working right. Still no. Let's see. Hold on one sec, guys. Maybe it's just not working on this side. Oh, there we go. It's taking forever. Okay, there they are. All right, so the first equation that deals with this stuff, first thing really we talked about yesterday out of all this was the velocity that we said the direction is always changing, right? So the velocity of something going in a circle, if we wanted in uniform circular motion, the uniform part of UCM means steady, all right? It's not that we can't speed up and slow down while going around a turn. It's just that since this is a new topic, we're going to make it as simple as possible and only study it right now when we're going at constant speed around the circle, okay? So real early in the year, when we, like the first equation we learned, most of you already heard of or knew, it was the formula for constant speed just in a straight line. Anytime we had something moving at constant speed in a straight line, what old formula did we use, guys? V equals d over t, right? Well, it might not look like it, but this is really v equals d over t. Just for a circle. What do we call the measurement of the outer path of a circle, geometrically? Krish? The circumference, right? Wouldn't you say when I'm swinging an object like this, or any object moving in a circle, that the distance around one time is the circumference, right? It's like a track, a path it's on, right? And one formula, somewhere in geometry, or even prior to that, probably well before that in the lower math, you learned that circumference is 2 pi times the radius, right? And by the way, we want radius in meters, so we have to convert it to that if it's not in it. So really, that's just a specific d, isn't it? It's the d for the path around a circle one time. And we usually in the past have written t for time with a little t, right? This is a more specific time. It's still a time, but we call it the time period. Like I have in parentheses over beside it, the time period isn't just any old time, like you might use for a linear motion, v equals d over t. It's the time for one full cycle or one full revolution. All right? So this really is just v equals d over t, just specific for a full circle. All right? So if you simply know the radius or the diameter, because obviously the diameter is twice the radius, that's where the 2r comes in here, and how long it takes to go around one time, if you just divide them, you essentially have that speed that you're uniformly traveling around the circle with in these circumstances. And just a FYI, and I think I mentioned this a moment ago, sometimes, since at every moment the vector arrow drawn for v is pointing tangent to the circle. Sometimes we refer to this as a tangential velocity. So when we use this formula to figure out v of this stopper, and then I let go, that's also the v it would fly off tangent to the path on until it hits something else. All right, the core equation for the centripetal acceleration. This is the acceleration that points towards the center, if you mark where it is. That is due to not speeding up or slowing down, but to changing direction. Its core formula is v squared over r. Now this formula, most of the time when I give you a new formula, I try to derive it or at least tell you where it came from. This one's a little more tricky. Pretty as simple of a formula it is, it's pretty complex mathematically where it comes from, so I'm not going to worry about that right now. Just know for right now, its centripetal acceleration is v squared. This same v that's up here, if we find it and plug it in here and divide by the radius, that ends up being the centripetal acceleration. Although it's a special kind of acceleration due to changing direction and not speeding up or slowing down, it still has the same units as always acceleration does in here. And what's that? Meters per second squared. This blue formula can sometimes be helpful. It's not 100% necessary, but in the right problem, it might help you like save a step. Basically, if I took this formula here, 2 pi r over t, and just substituted all that in algebraically for v, squared it and reduced everything and simplified it, it would become this formula in blue. All right, it's basically like smushing those two formulas together algebraically. I mean, you could get by without it, but I'm just throwing it in there already put together. It might help you on the problem if you aren't given v directly but need a and maybe given some of the other stuff in it. And finally, the last formula is one we already know, but just slightly tweaked. F net equals ma was Newton's what law? Second law. We just recently had finished all the stuff about that, right? The total force acting on an object on that axis is equal to mass times the acceleration on that axis, whatever specific axis, x or y, we were looking at, right? Now, for centripetal circular motion, we say the centripetal force equals mass times the centripetal acceleration. Most of the time, the centripetal force, as far as the problems we do in here, is just a single force. All right? This is, and I started yesterday like this, so I'll remind you of that, review that real quick too. This is what's known as a horizontal plane circle, because a circular path is in the horizontal plane, right? The x-plane. Most of the time, I don't want to say all the time, but most of the time, when using this formula, the centripetal force that goes here is usually one single specific force. The term centripetal force is pretty generic because it just means a force or forces that make something go in a circle. Usually, especially when solving a problem, we need to identify the specific centripetal force. In this case, it's tension. Sometimes your textbook refers to this as what the agent is. If you see that, which you probably will in a question or two, the agent means the specific force that is centripetal in the situation. All right? So when I asked a moment ago what force is making this go in a circle, if you said centripetal, you're not really wrong, but you're not being specific enough. It's going in a circle, so there has to be a centripetal force. Specifically, in that case, it is the string, the tension in the string. All right? Other forces we threw out yesterday that are commonly centripetal. Friction. When a car goes around a turn, if friction wasn't there, could you round a turn? No, you fly right off it. That's why the turn's icy. You fly right off, right? Normal force can provide a centripetal force to get you to the turn. It could be the normal force on a turn on a roller coaster from the track pushing back on you. A lot of amusement park rides from turning are normal forces on you. Okay? And gravity could even be one too. Now, still today and probably the rest of this week, we'll stick with problems on horizontal plane circles. But soon, next week, we'll get to vertical plane circles. And when we do vertical plane circles, gravity becomes a bigger factor because it's also on that axis, as we learned before, right? All right, so, but anyways, we're just, again, using Newton's second law, but the force or forces you put here have to be the ones that are causing the circular motion, okay, when we sub it into that. And that's it for the new formulas, but you'll also see some other older ones that we already knew might come back into play at times for certain problems. So those are all the brand new ones. So now we're going to go into one example, and I'm going to pick another one for a second example that's actually just a regular problem. So go to page 155. Once we get through these examples, I'll give you whatever time's left to work on the handful of problems I'm going to give you. Okay, example 2 on page 155 says a 13 gram, this is actually the same situation as what I was just flinging around here. Just a rubber stopper, any old mass, it doesn't matter what it is really, but we know the mass of what I'm swinging around is a 13 gram rubber stopper. It's attached to a 0.93 meter string. The stopper is swung in a horizontal circle, making 1 revolution in 1.18 seconds. Find the tension force exerted by the string on the stopper. All right, so as always, we start by listing givens, right? Now, one thing real quick. Do you remember? We always want masses in what unit? Kilograms. So that's in grams. If it is, we got to convert that. We'll do it right away. That would be 3 places to the left. That would be 0.013 kilograms. The string is 0.193 meters we're swinging it on. What is that telling us? What given is that telling us? Think about some of the variables in the new formulas you just wrote down. That must be the what of the circle? Gordon? The radius of the circle, exactly. Sometimes they'll throw in diameter. Obviously, we should know we have to cut it in half if it gives the diameter. Throw it in as radius. Just be aware to look out for that. So R equals 0.93 meters. If that was like in centimeters, make sure you convert the meters, but we're good here. The stopper is swung in a horizontal plane circle, making 1 revolution in 1.18 seconds. And that's exactly what we define big T time period is, right? The time it takes for 1 revolution, or 1 time around the circle. It then says, find the tension force exerted by the string on the stopper. So, of all the formulas we just showed you for circular motion, the only one that has force in it is this one, right? But here's where you got to sub in just what's specific to the particular problem. As I just explained a moment ago, the force that is centripetal in this particular situation, this problem, is the what force? What's making this go in a circle? The tension. So because that is the centripetal force, I could substitute it in here, right? The tension is the centripetal force. So the tension that it's asking me to solve for is equal to m times the centripetal acceleration. I don't know the centripetal acceleration, right? I could either solve it off to the side because I do have enough information above. I don't know v, so this is where that other formula I put in blue could come in handy. I do know r and t, though, and one of the formulas for centripetal acceleration was 4 pi squared. Obviously, pi is 3.14, right? 4 pi squared r over time period. We'll use that to find it. Once we find it, we could plug it in there, take it times its mass, and we got the force. So 4 pi squared times 0.93 divided by 1.18. Oh, t squared. Yes, sorry, I forgot it up there. R is not, though, because it reduced out in the algebra. Okay, once we run those numbers, we should get something pretty close to 26 meters per second squared. But just to understand what we found there, that's the acceleration that is being caused by moving in a circle. This is not speeding up or slowing down. This is being caused at centripetal by just simply changing direction constantly. Okay? And this is why human centrifuges are used to train for high G forces that could happen in like jets and space shuttles and stuff like that. It feels just like gravitational forces, even though it's not. All right, these G's caused from spinning, and most, not all, but most amusement park rides, especially roller coasters, cause varying G forces. G forces, way back when we described as kind of a bad term, because they're not really forces, they're accelerations, because we know little g is an acceleration due to gravity, right? So if we wanted to figure out how many g's, this is just a little extra, it didn't ask in this problem. If we want to figure out from what we just found how many g's this stopper is experiencing, 1 g is 9.8 on Earth, right? So if we took 26 that we just found here, divided by 9.8, I get about 2.7 if I round. So it's this rubber stopper, if I'm swinging it like with all the features given here, it's experiencing 2.7 Gs. Those are multiples of 1 G, which we know 1 G is 9.8. So when you ever like are in line for a roller coaster, and they usually have, because you wait forever for them sometimes, right? They usually have a big board that gives you information about the ride, and a lot of times it will tell you the maximum Gs you might experience on that ride. So if you read it and it says you may experience up to 2.5 Gs or something like that, that means at times. That doesn't mean the whole time you experience that. In brief moments, you could experience up to that. And that means you're really feeling accelerations on you that are 2.5 times the normal that you regularly just feel for being on Earth. Right? And again, pilots, astronauts could feel, possibly at times feel up to 9 or greater Gs. And if you're not trained for that many, it does a lot of stuff with blood flow inside your body, and you could easily pass out. You could even die from them if it happens too long. So they have to train for it, learn special breathing techniques, things like that, in order to keep oxygen to their brain because of the feelings of all this stuff. But anyway, that's just some little extra FYI stuff. Are you guys here Friday? Yeah. If we get done with everything for the week with a little extra time Friday, I might talk a little bit more about that. We'll see. Okay, so with this acceleration then, finishing off the problem should be pretty easy. Just bringing this equation down here. Now that we know the acceleration, I just take it times the mass through this version in Newton's second law. And the mass that we already converted is 0.013 times the 26. And that gives us about 0.34 newtons of tension in the string. Any questions on anything we did there? All right, there's one more problem I want you to try, or want us to do together. And it's actually in the back of the chapter. Number 65 on page 166. Find that one. It says, friction provides the force needed for a car to travel around a flat racetrack. All right? And as a matter of fact, this is actually simplifying something. There's not many flat racetracks out there. Even roads, when you think about it, many roads aren't even flat. Around turns especially. What do they do to turns to, how do they engineer turns to be a little more safe? Go ahead. They're banked, exactly. You just described they're banked. They're put at an angle. Because when you bank a turn, then not just friction helps you get around it. Part of a partial normal force helps you. Because being banked at an angle, some of the road actually pushes you towards the center of the turn, the theoretical center of the turn. On a flat turn, we should know from the past that the normal force only points directly up. And around a normal turn on a flat road, is the turn upward? No, it's this way. So the normal force doesn't help you really at all. directly, I guess you could say, on a flat turn. So that's why when you see like NASCAR tracks, especially cars that are going 200 some miles per hour, they have extreme banking. If they didn't, it would be a really boring race. Because, well, depends on how you look at it. If they tried to go that fast, it might be exciting because they'd all fly off the road. But if they didn't want to fly off, it would be really boring because they'd have to go very slow to not fly off around those radius turns. So the banking angles are very steep. But if you think about driving around places you've experienced, the highest bank nor typical turns are usually on ramps or especially off ramps of the highway, right? Because why are they banked there more compared to other places? A lot of people just don't follow that slow down to 25 miles per hour thing when you're getting off a ramp. A lot of people go almost the same as that they were going off, at least for a little while, around those turns. And if they were flat and not banked, that would mean only friction holds you on that turn. And you would fly off very easily unless you slowed down a lot. All right, so that's a little background into this. But this is a flat turn. So the only thing holding us on, like this problem says, is friction. It says, what's the maximum speed at which a car can safely travel if the radius of the track is 80 meters and the coefficient of friction is 0.4? All right, so our givens are, let's jot those down. The radius is directly given as 80 meters. The coefficient of friction, and we should remember from recently that there's two types of friction. What were they again? Kinetic, and what's the other type of friction? Now this is called, mu is the coefficient, but there's two types of it. Therefore, static and kinetic, right? So, it said, what's the maximum speed for the car to safely travel? So which kind of friction is it probably talking about, kinetic or static? What do you think? What are you doing if you're in kinetic friction? You're doing what? Okay. Be more specific. Sliding. If you're sliding through a turn, do you think that's safely moving through the turn? No. So what type of friction should we assume this is? Static. Make sense to everybody? Because if it was kinetic, that wouldn't be very safe at all. So they must be talking about static. 0.4. Remember, this is the number between 0 and 1 typically that we learned about in the past chapter. Okay? All right, so it doesn't look like it gave us that much. And our goal is to find the maximum V that we could travel around this turn with this amount of coefficient of friction. And one more time, just to refresh ourselves, coefficient of friction is like the value that the higher it is, the higher the friction is going to be between, in this case, the road and your tires. Right? It's not the force of friction, but it greatly affects the force of friction, right? All right, it's like the roughness or smoothness between the two things, as we said in the past. All right, so anyways, where does that come in with only that? It all starts with Newton's second law and intertwining this new stuff with stuff about friction. So let's start again with that, and you'll see why I do that. I don't seem to have any of that, do I? But what is the specific centripetal force in this example? Friction, right? So I'm going to replace this with friction, specifically static friction, because as we said, we're going through safely, right? So static friction will equal m times the centripetal acceleration. That still doesn't really help me because I still don't have a v to solve for, do I? So I'm going to make some more formula substitutions. Remember we said one of the core formulas, the core formula for centripetal acceleration is v squared over r, right? So all I'm doing is subbing in that here. I'll just write it off this side just to show it more clearly. That's one of our new formulas. So if AC's here, I could sub all that in there, and that gives me this. Everybody with me? And again, once you see this fully, you could skip a lot of these steps, but I want to break it down one little step at a time. Okay, well, I finally got a V to solve for, right? I do have R, but they never gave me mass, did they? I had to keep subbing. Something old. What is the formula for force of static friction, maximum force of static friction? I'll start it. Mu times what? We just used this a ton recently, right before break. Friction is, the force of friction is the coefficient times what force, guys? Normal force. Remember that? All right. I'm not fully there yet, because I still have M. But on a flat surface, because this is a flat turn, right? In the past, we always said normal force equals the what of the object. Just last chapter. Since this surface is flat, if this car weighed 8,000 newtons, what's the normal force on it? 8,000 newtons, right? So what we always said in the past was that on a flat surface, as long as nothing crazy is going on, the normal force equals the weight, right? What does weight equal? M times little g, right? And that now solves the problem of mass being around, because what can mass do, guys? Cancel out. Once mass cancels out, I algebraically solve for V by multiplying R to the other side and taking the square root. V equals the square root of mu G times R. Plug in those numbers, and that's going to be the mu was 0.4. We always know little g is 9.8, and the radius was given as 80 meters. Yeah, around this thing. We run those numbers, and you should get something close to 18 meters per second. Just to save time, I'm cheating a little bit and looking at the answer in the book, so that's the sig fig answer. It might be more like 17 point something, okay? I know we made a lot of substitutions there, and really, once you fully understand this, you don't have to show every one of those little steps. If you go from like here to the final equation, as long as you know why, that's completely fine with me, okay? Is there any questions on anything I did right there? Had to remember a decent bit of old stuff right there to be able to solve this problem. All right, if we're good with that, I posted on yesterday's post the problems that I noted did not start them till after we got this far, okay? So I want you to go back to the post from yesterday. The problems are listed there. I believe there's 6 of them. I want them all attempted for tomorrow. Like always, it's not for right and wrong. Just attempt them all. Do them on Squid like we've been, because obviously you're not here tomorrow. Tomorrow, though, with the people that are here, I'm going to go over every one of them. I'll post that video. Just make sure you're good, and you turn them in, have them turned in like before class time tomorrow, okay? Yeah. You good? Yeah, don't forget that. But all these should be similar enough to these examples. I think you should be all right. Okay. The little bit of time you have left, you can start them right now.